I will talk about the inverse Sturluville problem on a half line. My name is Briceyda, and this is a joint work with Vladislav Kravchenko and Kira Kalmeskaya. This is the structure for the seminar. I will start with a definition of the classical inverse Sturluville problem. After, I will give the definition of transmutation operator, and I will pass with the famous Gelfand-Levitan equation. The last part is concerning the Fourier-Legendre series representation given by Kravchenko and his colleagues. And we will employ this for give a numerical method and solve the inverse problem. Okay. We consider the classical inverse Sturluville problem a half line, and it consists in given an spectral density function sigma of the spectral parameter, finding the potential Q and the number H such that the density function be a spectral density function of the following Cauchy problem. Here we have the Sturluville equation, and the boundary conditions are given at 0. Okay. For this work, we will suppose the following hypothesis. H must be a real number. The potential is a real value function, and satisfy that when we multiply 1 plus x by the potential, this new function belongs to the Lebesgue space L1. And the last condition is the normalization for the sigma function. So it is well known that the Cauchy problem that we saw, this one, has a unique solution, and we will denote it by phi. Okay, if we start with E, a linear topological space, and E1, a subspace of E, and we consider two linear operators A and B defined on E1, we will say that T is a transmutation operator for A and B if first E1 is invariant under T, also T and his inverse are continuous operators, and the last condition is that the following relation holds. A by T is equal to T by B. So we are looking for an operator related for, in particular for A and B differential operators, which satisfy these three conditions. Okay, the first one is included here. I don't put like a point, but it's this one, the first one. Okay, and some straightforward consequence for this definition is that the image of the transmutation operator restricted to the spectral of B is contained in the spectral of A, and the image of the transmutation operator restricted to the kernel of B is contained in the kernel of A. So one of the most important applications for transmutation operator is to relate a simple differential equation whose solutions are known with another more complicated differential equation. And this concept of transmutation operator was proposed by Delgado in 1938 in this work one. And this idea was extended by him and Lyons in the 1956. So here are the reference. Later in 1948, Posner proved that the transmutation operator that relates the Sturluville equation with this equation B, second derivative of B plus lambda B equal to 0, this transmutation operator can be written like a Volterra integral operator of the second kind. So, and this result we will use for this inverse problem. We will use this expression for the transmutation operator. Okay, here we have In other words, we have the same example. E is equal to the Schrodinger operator, B this second order operator. Then here are the expression for the transmutation operator T. And this is the expression that we will use. And we can notice here that everything is now except by the kernel, transmutation kernel G. So there are different methods for the construction of G, but we will use in particular one called Fourier-Legendre series representation. We will see later what it means, this series representation for the kernel. And okay, this transmutation operator satisfies this relation. The operator A by T is equal to operator T by B. Okay. The solution phi that we saw at the beginning for the Sturlupil problem, here I repeat the Cauchy problem, admits the representation, then the solution phi can be written like the operator, the transmutation operator applied to the cosine function, evaluated in the square root of lambda of the spectral parameter multiplied by x. So here we have the expression is the operator T applied to cosine. So again, everything here is known except by the transmutation kernel G. And what properties satisfy G? For instance, G is a continuous real value function, and it has the same smoothness than the integral of the potential Q. Okay. For this part of the spectral theory, I am following the reference, the monographs of the authors Jurko and Freilin and Jurko. Here are the exact reference. So thanks to the condition imposed on the potential Q, it is well known that the discrete spectrum for the forward Sturm-Liouville problem on the half-line is finite and negative. So if we denote the set of the spectral data like this, here B will be a continuous and positive function, lambda sub n and alpha sub n will be the eigenvalues and the corresponding normalized constants, and the expression for these constants is given here. So now we are going to define the function f, which contains the spectral data of the inverse Sturlupil problem. Here we have f is equal to the integral of this multiplication of cosine functions, and here in the differential we have the information, the spectral data here. We will have that this sigma is equal, for lambda positive will be the function b minus 1 over p by rho, and for the values in the discrete spectrum, we will have that this sigma function will be equal to the normalized constants that we saw in the previous slide. Now this is a famous result. It's called the Gelfand-Levitan equation. This is equation 2. And it tells us that the transmutation kernel G satisfies the following Fred-Hall integral equation. So this G is the transmutation kernel, and F is the function that we saw previously that contains the information of the spectral data. So if we rewrite the equation 2, we can write it like G equal to minus the operator, the transmutation operator T applied to F. So hence the function F is the pre-image of G under the transmutation operator T. And you can find this result also in the monograph of Freilin and Jurko, and also in the Levitan's book here. Okay, another ingredient that we will need for our construction or numerical method, one part is this Gelfand-Levitan equation, and the other part is the Fourier-Legendre series representation. In this paper, representation of solution to the one-dimensional Schrödinger equation in terms of Newman series of Bessel function of the authors Kravchenko, Navarro, and Torba, they prove that the transmutation kernel G admits a Fourier-Legendre series representation, and this is the expression for the series. Here, the P sub n will be the Legendre polynomials of order n, and these coefficients can be coefficients an can be constructed by a recurrent integration procedure. I don't include the formulas here for the coefficients, but if you are interested in the exact formulas, you can look at the paper. I just put the expression for the first coefficient A0 because this will be the only data that we need for solve the inverse problem. Only the first coefficient will be needed. And okay, we can see easily that A0 is equal to the solution of the Cauchy problem evaluated at 0 minus 1. If we take the spectral parameter equal to 0, then the solution phi at 0 satisfies this reduced equation. The second derivative of phi evaluated at 0 equal to the potential multiplied by the solution at 0. And we already know that we have an expression which relates the first coefficient with the solution at 0. And if we derivate twice this expression, we will have, and we clear the potential here, we can recover the potential only in terms of the first coefficient. The potential will be the second derivative of the first coefficient divided by the first coefficient plus 1. So, and this expression will we use in the numerical method. And moreover, the boundary condition of the derivative h will be the first derivative of the first coefficient of the Legendre series, Fourier-Legendre series representation. In summary, the inverse Sturluville problem reduced to finding the coefficient A0. Okay, now we have this theorem. Okay. This theorem tells us that the coefficient of this Fourier-Legendre series representation satisfies the system of the equation. Here we have a system, and here we have, recall EM are the coefficient of the series. These new functions A sub mn and F sub m are defined like following. The first one is the integral of the product of these two spherical Bessel function, and Fn is equal to the integral of the product of the spherical Bessel function multiplied by the cosine function. Both are with the same density function that we saw in the previous slide. Okay, this result you can find it in this paper. It was published in 2019. Okay, I don't give the proof, the complete proof. I just give a sketch of the proof. And the ideas are the following. If we take the series Fourier Legendre representation and we substitute in the Gelfand-Levitan equation, we will get an expression like this. Here is the substitution done. And here appears the Legendre polynomials, and we know that these Legendre polynomials is an orthogonal basis of the space L2. So for this reason, we can use many properties like the Parseval identity. We can use that that we know the norm of these Legendre polynomials. We know that they are orthogonal when n is different to n, and so on. In particular, we have the following formula. We can use the following formula, which represent the spherical Besson function in terms like an inner product in L2 of the cosine function multiplied by the Legendre polynomial. So we can use this expression and combine this here, use a kind of a Fubini theorem here, because we have an expression of f, interchange the integrals here, use this formula, and we reduce this expression into the following one. We will have an expression like this. And this second term that appears here in the left-hand side, this term, is exactly the function f sub n that we define in the statement of the theorem. So the convergence of the series this series comes from the Parseval identity. Okay, something is missing here, but okay. This expression will be equal to the inner product between f and g, because by the Parseval identity, this inner product is equal to this expression. Here we are taking the product of this product, and here we are using this is an orthogonal basis. And if we use the orthogonality here, we will have that this expression will be exactly the coefficients, the series of the coefficient divided by x, and this expression will be exactly the function f sub n. Then this series will be equal to this inner product, but that's here it doesn't appear the equality. So okay, and this is the sketch for the proof. Okay, now having this system of equation, we can truncate here the system. We can consider only the truncated series here until number m fixed, and we can solve this m by m system of equations. Okay, and now the previous theorem provides a simple and direct method to solve the inverse SWB problem on the half-plane. The steps are: first step, compute this truncated function a and f sub n are exactly the same expression that we saw in the statement of the theorem, but here we are taking, instead of taking the integral from minus infinity to infinity, we are taking in the continuous spectrum from 0 to lambda, to capital lambda here. I will say later who is this capital lambda. And here for the discrete spectrum, you can put only the this x is the variable. It's not a times symbol. It's the variable. Okay. Here is include the information for the discrete spectrum. We just separate the continuous and the discrete part. And okay, we have this truncated function. Now, we will choose a set of points on the interval 0, b. And for these points, we solve point-wise the system. It's the same, but here is just truncated the system of equation until m. So after to solve it, we will have an m by m system of equations. So we only need the A0 coefficient obtained from here, and we can recover the potential. The recovered potential can be denoted by q tilde and will be A0 second derivative of 0 divided by A0 plus 1. So, and all this information comes from the system. Also, the capital lambda was taken in this numerical method inversely proportional to x, which means that for a fixed p positive, capital lambda was at the point s, x is equal to p divided by x. Okay, and now I am going to finish with an example. If we consider the potential Q equal to this expression and the boundary condition H equal to 0, then the function B at lambda has this explicit expression like this. Well, this example was taken for the paper construction of the half-line potential from the Jost solution from the author Actoson. And he gave this explicit expression for B using the Jost solution, the theory provided by the Jost solution of the Sturm-Liouville problem. So in this example, we can see that the discrete spectrum is empty. So then the truncated expression here, this part disappears in both, and we only need to compute this part. For the fixed capital lambda inversely proportional to x, we compute this expression with the function b provided by the paper of Actoson, and we, after compute this system of equation, we get A0 and we compute the recovered potential. So if we compare the recovered potential with the real potential, then the maximal approximation error of this recovered potential, you can see in the table that, for instance, for m equal to 5, we have this maximal error equal to 3.5068 by 10 to the minus 5, which is considerable small. Only considering m equal to 5, which means a 5 by 5 system of equation. So thank you for your attention.